right, then we are good to go. Hello and welcome everyone. Thanks for joining this session. I just talked to Mark. I've been here at DevVox in 2023. I'm happy to be here today again at this year's DevVox with my talk, End-to-End Encryption for Streaming Data Pipelines. My name is Hans-Peter Grasl. I work at a company called Decodable, where we are building a fully managed real-time data platform, which is built primarily on top of, I think, widely deployed, battle-tested, and really popular open source technologies. First and foremost, Apache Flink as the stream processing backbone, basically. There is some Kafka, there is Debezium and change data capture in it. A bunch of things that people usually know about when they are doing some stuff in this area of real-time and distributed data processing. Today's talk, however, is not so much about Decodable or the great product we are building there. Instead, I want to share with you a data security related topic which I started to work on almost 4 years ago already now. And so yes, there will be a bunch of Kafka and Flink, also Debezium in the demo that I'm going to show you. But again, this is just focusing on essentially open source. And I created that open source project out of some ideas that evolved from my experiments, which is called Kryptonite for Kafka. And this is what I also want to introduce you during this talk. But before doing that, I think it's helpful to remind ourselves when we build streaming data pipelines and we build workloads on top of Kafka, what are the usual things that we want to make sure in terms of securing our data that is produced to and consumed from Kafka. And this essentially boils down to enforcing 3 vital, basically core security measures that you want to have in place, that I just want to quickly go over because I think most of you know about these concepts, maybe not necessarily from Kafka context, but from other systems you have worked with. First, there is, of course, a traffic encryption. We need to make sure as our data from a data pipeline goes into Kafka, produced by some Kafka client, is secured when it travels over the network. We typically do that by employing some means of TLS encryption. Why do we want to do that? So that nobody eavesdrops on the data and nobody can tamper with the data as it flows from my Kafka client to a broker. So that's, I think, well-known concept anyway. Then we have second, authentication. We need to understand or identify communicating parties among each other. So Kafka clients again and Kafka brokers, different options to choose from. SASL, multiple flavors, SASL plain, SSL. You can do mutual authentication between brokers and clients, most likely using certificates again with MTLS. You can do, there are vendor extensions, like if you need to integrate in enterprise context with Kerberos or whatever, there's GSS API and all those things. But what matters is that you figure out a way that you identify clients that talk to these brokers. And third, you have an authorization layer in place that you can, once clients are identified and you know, or at least you think you know who it is that talks to the broker, you can either allow or deny certain operations, right? And again, just a few simple examples. This is so that not every client is allowed to read from arbitrary topics, or not every client should be allowed to create new topics, or let alone delete topics and things like that. You get the idea. So some form of authorization. And again, in Kafka, you have access control lists, you have in some vendor distributions, you have more fine-grained options, role-based access control, and things like that. This is table stakes, and I hope we essentially all agree that getting these 3 things right for any serious production workload, any serious streaming pipeline that you would build on top of Kafka, this is something that you absolutely want to have. There is no excuse, in my opinion, whatsoever, that you can completely abandon any of these 3 things. The question remains, though, is this always sufficient? Is it always sufficient to have network encryption, authentication, and authorization when building out data pipelines on top of Kafka? And the usual answer to that is it depends, right? And that's not a wrong answer. That is very rarely a wrong answer. But I think you can well anticipate my own personal view on that. And I claim that no, in general, it is not always sufficient to have these things. And in order to understand why, I think it's worth to look at one specific gap in that security model when we would think about it from a threat modeling perspective. So at one end of our communication, we have network encryption. We had that. I just mentioned that. At the other end, so whenever brokers get that data and store it in topics, at some point this is persisted to some storage. And then we have storage encryption. I didn't talk about that yet, but this is various different forms again, something that we could summarize as encryption at rest, basically. So you could have volume-based encryption, disk encryption, file-based encryption, all sorts of things to make sure that the data that is stored persistently somewhere is encrypted. But the question is, what is in between these two things? And with in between these two, I mean whenever our data is in actual use, in this case by Kafka brokers. And the answer to that is actually quite simple, even though not everyone likes or wants to hear it, but the answer to that question is that by default, every Kafka broker gets to see the plaintext payload at some point before it then gets written to some sort of persistent storage. So there's no way in out of the box when working with Kafka or open source Kafka to prevent brokers from seeing very sensitive data. The same holds true for any legitimate Kafka client, and with that I mean, of course, that any client that successfully authenticated and follows its access control rules, still, when a client is allowed to read from a specific topic, it is always allowed to read every message, and it is always allowed to see all the fields in any Kafka record of a particular message in that topic. So you cannot prevent and say, well, there's 2 fields that you are not allowed to see. So that being said, wouldn't it be nice to have something like real end-to-end encryption? And with that, I mean something where a specific Kafka application can send data to Kafka, and another Kafka application is allowed to see all of its data, but nowhere in between for the brokers or anyone else is it possible to see all of the fields in plain text. And this is actually what led to these experiments I did already 4 years ago, and later then created a little open source project for, which is called Kryptonite for Kafka. And this is what I want to show you also in a quick demo, how you can use it to build such an end-to-end encrypted streaming data flow on top of Kafka. So what it gives you in a nutshell is what I call client-side field-level cryptography. And this may not ring a bell for some of you, and that's okay, but bear with me after the talk. I think you know exactly what that basically means and how you could use, for instance, this project of mine to implement that and put this into practice. First, the term client-side. What client-side means is that any encryption or decryption operation on very sensitive data in my Kafka records are only ever happening at the client side. So the brokers don't care, the brokers don't even know, the brokers are never involved in any form of encryption operations on a payload level. All of that happens on the client side. Also, the cryptographic keys that you use for that are never existing or never accessible to the broker infrastructure. Then field level. Field level means that we, instead of just saying, well, let's take the whole payload as is and encrypt it into one big chunk of ciphertext, we want to precisely define and control, looking at some payload here, which part or parts of a particular Kafka message should get encrypted, or should get, in this case, this extra layer of data protection. And here we see a very simple JSON payload example, where one field, the SSN, the social security number, should never be or should never leave, in this case, the client application in unencrypted form. And so then the idea is that you find a way to only encrypt this particular field. Everything else in that message stays as is. So what you end up with is in like generally speaking, something that you could call a partially encrypted payload. And then any consuming client that is not allowed to see it or doesn't have access to the secret key material would see the partially encrypted record. So some of those fields are available in plain text, others are not. The first thing where I thought it makes sense to have that, because it's also, if you think about it, a very convenient way to start working with this idea, is in terms of Kafka Connect, where Kafka Connect, if you don't know it, is a data integration framework, and there is many connectors out there to connect to various source systems and sync systems and exchange data over Kafka brokers. And it has this concept of single message transforms, and my project, in fact, implements one such single message transform that does the field level encryption. So in this model, basically, you could take any Kafka source connector to talk to a database, to read from files, to read from APIs that you want to use to send data into Kafka. And then in addition to what you do with the source connector, you configure the Kryptonite transformation, which takes care of doing that field level encryption. So Kafka Kafka Connect writes partially encrypted data already to the brokers. How can this look like? First, a simple demo. We take data from MongoDB, so some documents are stored there. We use well-established Kafka connector from the Debezium project, MongoDB source connector in this case, and then we combine it with this Kryptonite transformation so that we get this partial payload encryption. And this is what I want to quickly show you how this could look like in that demo scenario. So I have a bunch of containers, so everything runs locally here on my machine. For now, it's only relevant to start looking into the documents that we have in MongoDB. I'm not sure if you can read that from the back. Let me make it a little bit bigger. So I will mark one of them. So this is one fictional record of some personal data, right? So I hope nobody recognizes themselves in this data. It's just pure coincidence. If it would happen, this is fake data. But still, there is a bunch of, personally identifiable information in there that you do not want maybe to send to a Kafka topic in that way. And so we can instruct, again, the Kryptonite plugin to take action. So once I started the Debezium source connector for Mongo in the background, and it reads the data, and then before it writes it passes it through this transformation. And the configuration for that transformation is just 4 or 5 lines of additional configuration that you need in order to do this partial message encryption here. So first of all, we tell it what is the transformation itself, then it should encrypt, then we tell it where to find the secret keys. In this case, it's a simplified example, so the keys are mounted into the containers file system, which is something that you may not want to do in practice, but you can imagine that you can read these keys, for instance, from a cloud KMS. Azure Keyword Support is something that I implemented for doing that, so that the secret key material resides elsewhere, and or the key management itself is not based on files like here, but is done in a more enterprise ready way. And then you have a key identifier which tells the system, okay, if you don't specify any specific key, what should be the default key to encrypt any kind of data? And then you tell it what fields it should encrypt in the field config here. So basically, we see that we have different options here. We can not only refer to single fields on the top level, we can also reach into the structure and say we want to encrypt this sub-document element-wise. And we want to, for instance, encrypt the height, the eye color, the age, and a bunch of other things individually. We can also say no, for the contact information, like here, email and phone. We can also say just take whatever the content field represents and encrypt it in one chunk. So basically what's called object level encryption here. And finally, we see that we can instruct it to also encrypt individual array elements, meaning it would understand that it has to encrypt those 3 addresses here in that particular record individually. So what we end up with when we look into a Kafka topic with a standard consumer is with a payload like this. You see very few fields are left in plain text, basically the first name, the gender, the active flag, and the registration date. Everything else in this case was encrypted on a field level because we said we don't want to send this information in unencrypted form to any Kafka topic. We also see again here this differentiation. For context, we have one chunk of ciphertext here. Again, the reason what you see here is basically the base 64 encoded version of the ciphertext. So basically all encrypted fields become strings. And here on the other hand, we see this element-wise encryption. So here we just know there are two known residences, but we cannot really access the actual address information without having access to the secret key. So much about bringing in data from various sources into Kafka topics with essentially just a bunch of additional configurations on top of already existing Kafka, in this case, source connectors. So the next thing then was that some people found that useful after I put it on GitHub and then asked, hey, could we maybe think about having something like that, but for stream processing, where we want to actually process data. We just don't want to move it from A to B. We want to act on the data. Maybe you want to do any type of processing that you want to do in between your source and sink system. And so the first thing I did back then was to bring support for KSQLDB and user-defined functions for KSQLDB. Again, the main idea was to keep it simple to use. So declarative approach in SQL makes a lot of sense in this case. After that, I thought about why not have the same thing in Flink context. So you may know that in Apache Flink, you can also declare your stream processing jobs by writing SQL. And it has the same concept of user-defined functions. And so the idea then was to bring user-defined functions for encryption and decryption such that you can use that from within a SQL job. The way this works is that in Flink, for instance, you would create a table, a Flink table. You would define some schema. And then you have this table concept. And then you could write into that table, either by insert statements or by selecting from some other tables that you feed some derived data into a new table and stuff like that. But instead of doing that with the actual plain text values, again, you can apply encryption and decryption operations accordingly. Here we encrypt similar to what we had before in the example. We encrypt the social security number. And then again, Flink under the covers, in this case using a Kafka connector, would persist this table into a Kafka topic. But again, from the Flink job, out of the Flink job would only ever come this partially encrypted record. Conversely, if another Flink job should be allowed to work with some of the data, hence gets access to the secret key material, it can define the table and it can then decide, hey, I need the SSN in plain text, so it can basically apply a decrypt function on that column to effectively decrypt all of the values in these rows, again, from the convenience of writing SQL. So the way this works here is demo part 2. We want to pick up the data that was ingested from this Kafka source connector, and we want to keep processing it, in this case with Apache Flink SQL. And so we will see that we can take that data, we can do some interesting calculations on top of that encrypted data in that Flink job. And also if that Flink job maybe creates new derived data that needs to go into a separate table and contains sensitive data, again, it could encrypt the data on the way back into a new Kafka topic. You get the idea, I guess. Let me show that to you as well real quick. So I go into the SQL, interactive SQL shell here from Flink. And I'm going to define a table right there. Let me copy that in. This table represents the same records that we just saw being ingested from Kafka source connector. And so if I were to say select star from tfake citizens in that Flink job now, you would see unsurprisingly, something similar to the plain consumer we have seen earlier. We just see very few data fields in unencrypted form. Everything else expectedly here is essentially this partially encrypted data. So what could we do with that? So obviously we want to act on some of this encrypted data, and so one example would be to say, let's so that we have something to process here. Let's say we want to figure out what is the age distribution across these personal records per eye color. So we could first write a subquery here that decrypts the eye color and the age fields of that Flink table, and then in the outer query just run a normal group by on the eye color and then use these simple aggregate functions to get back the results. Let me do that real quick here. We can do that. And then what happens is that Flink runs this job on the fly. It decrypts all of this data that we instructed it to, and we can get a simple statistic like that based on originally encrypted fields that come from that partially encrypted Kafka topic. We can also, of course, to see how we could handle arrays, we can also look at another example. Here we are interested in this array of known addresses, so we can instruct it to decrypt an array that has these elements, or the elements it contains are encrypted again originally. Then we want to flatten that array. We want to basically get a new table row per entry in that array using this unnest function. And then we can start to, in this case, again, these are just examples how to process encrypted data. What it does is then for each address, it applies this regular expression on the plain address string then, and figures out the state information of that address, so that we could say, let's figure out in all of those encrypted residences how much of them are in which particular US state. And again, the data set is quite uniformly distributed, hence you see it just switches between 5 or 6. But again, you can nicely see that also for these partially encrypted array elements, you can do some processing if this Flink client is allowed to access those secret keys. Finally, just another job that not only shows me like temporary results like in these queries, but creates a derived table and writes data back to Kafka. And again, so to show that we can also encrypt data on the way back, of course, from that Flink job. Let me first run it, and then while it runs, I briefly explain you what happens here. Again, we have a subquery, and that subquery prepares our data. We select from this original Kafka topic. Most of the fields have been encrypted, so we decrypt them, that we can later do some calculation. We need weight and height information of each person. For instance, we decrypt the last name, concatenate it with the plain text first name, and then say we want a new field that contains the full name, but the full name shouldn't be disclosed in the Kafka topic, so we can re-encrypt that concatenated string to have an encrypted full name. And we can also reach into the arrays and extract the last element, do some processing, and say the last in the array is the current residence of a person, and then encrypt it back so that the current residence, again, never gets written as plain text into that Kafka topic. And up there, with the decrypted weight and height information, we could feed that into that formula that tells us about the weight category of a person using the body mass index formula. If we do that, we see that, let me go out of that. And again, if we now were to inspect what Flink just created and wrote to Kafka with a normal console consumer, for instance, we would see the expected result, right? We get the BMI category and the age, and the field's full name and current residence for each of these records is not disclosed anymore. And it needs, again, some client that is allowed to see that in order to get back the original value. So this is how, just a few simple ways how you could use this concept of encrypting and decrypting payload fields explicitly from the convenience of SQL, and in this case it was Flink SQL jobs that we were running. With that, let me go back to the slides and show you the last part, right? The last part, the third part that is still missing from this end-to-end streaming pipeline is the sync side. And here, similar to earlier, we can use Kafka Connect, and in this case, sync connectors. They support the same concept of these transformations. So this is very similar to what we have seen for the source side already. If we want to say now some of the data that is partially encrypted in Kafka should go to a destination of my choice where it should be in plain text again, we can decrypt it, on the way out. Again, all we do is we take existing sync connectors, pretty much any sync connector for Kafka that you have, combine it with this kryptonite transformation, and you could achieve that decryption on the way out of Kafka, again, by means of configuration only. So this is what DemoBAT 3 does. It picks up now this data that was written from the Flink job into that new Kafka topic with these records with age, weight category, full name, and current residence, and writes it into an S3 bucket. In my case, everything runs locally, so this is just a MinIO container that runs on my machine, but the concept is the same. I'm using an existing sync connector from the Apache Camel family here for MinIO, and again, I combine it with the SMD to achieve the desired results. If we look at the configuration of the SMD only, it's just 4 lines again. We refer it to the SMT in question. We say, please decrypt the data now. Again, here is where you find the keys for that, and then we tell it which fields we want to decrypt. And again, just to highlight that there's no need to that this is an all or nothing approach. You can also have good reasons to only, in this case, say, no, we only need to decrypt the residence, but not the name, or the other way around. So essentially, any subset of the fields that are encrypted, you can decide to decrypt or not. So if that worked, let me just bring up the browser here. We should have some elements in that bucket from now, 1506. And I take any of them, just representing one such payload. Let me open that real quick. And yes, we see that on the way out, we decrypted the residence and the full name while writing that into S3 storage. That basically concludes the demo. I have about 2.5 minutes left. So we have seen that we can go from source to sync and do stream processing in between, and nowhere along this chain was any sensitive data ever exposed to, in this case, our messaging backbone, which was Kafka. I couldn't show you several configuration options. I couldn't show you implementation details or talk about them. But if you are interested in that, feel free to check out this project, which is the Kryptonite project here. Anything like reporting issues, opening tickets, whatever, anything that helps make it better and bring it forward is welcome, of course. And I'm happy if we have some time. I think 1.5 minutes, maybe we have time for 1 or 2 questions. And then I'm happy, of course, to take them right now, or you can always talk to me afterwards about this stuff, about stream processing in general, Kafka, Debezium, whatever you're interested in. I'm happy to chat about. Other than that, I thank you so much for coming and listening. Wish you a great rest of the conference, and thanks to the organizers also for having me. Thank you.